Okay, so for fluid dynamics, I have two additional sample problems. Let's take a look at the first one. I don't think there is a need for me to go through this problem in all details with you because we went over a similar problem, a classic Torricelli problem in the video lecture. It's also in the textbook. So basically you have a beer barrel with a hole at the end, and the top of the barrel is open, so it's exposed to the outside air pressure. And you're looking for the speed of the beer coming out of the hole at the bottom. You can also find the time it takes for the beer barrel to get empty. This sample problem just add one more twist, and that is it's no longer closed, open at the top. Rather, we have a heavy cylinder. Okay, we have a heavy, actually, cylindrical cap, which is this guy right here. Hold on, this guy right here. Okay, and it is airtight, and it can move along the cylinder frictionlessly as the beer barrel level changes. So the only difference this one introduces is that it has its own weight. It's actually pretty heavy, and because of that, it adds more pressure to the top of the fluid. And so when you have pressure P naught, the outside air pressure, and you have the pressure P here from P1 from the top of the fluid, P1 and P naught are no longer equal to each other. Rather, you need to overcome, P1 need to overcome not only P naught, but the weight of the cylinder. So you would have P naught A, that's the force from the air pushing the cylinder down, plus its own weight, which is mg, and then minus P1A, that is the force from the bottom of the cylinder, which is also the top of the fluid, pushing it up. That is the net force acting on the cylinder, and that should be equal to mass times acceleration for the cylinder, m times acceleration. The acceleration, in fact, can also be written as a second derivative of y as a function of time, and this y is the height of the cylinder of the beer. Now, assuming that that the hole at the bottom is very small, right? Then even though the beer barrel, the beer level descends, so y decreases, it does so extremely slowly. And as a result, the second derivative of y also is a very small quantity, therefore it is roughly equal to 0. Now that is a very important approximation, otherwise the problem is much harder, okay? And because of that, you can solve for P1. So P1 is simply equal to P naught plus mg over A. Okay, and the rest is the same as the problem we did. So you just replace P naught, you replace P1 from the original formula of P naught when the top of the barrel is open with this new expression of P naught plus mg over A, and the rest should be the same. You can find a numerical value as well. Now you notice that in order to make a difference, make a sizable difference in P1, you need a very heavy cylinder, okay, cylindrical cap. In this case, I gave a number of 460 kilograms. That's very, very heavy. And if you just use a regular, regular cap that you can lift, it doesn't really produce any noticeable difference in the pressure between P1 and P naught. So the air pressure really is extremely high. Okay, so that's the first problem. You can do the rest yourself. We're more interested in solving the second problem. Okay, this problem is about a very clever design of what's called a water clock. You know, there are all kinds of water clocks. They have pretty much the same basic function, that is, they use the movement of water to tell time. But in this case, you have a container of a certain shape. Okay, and it's cylindrical. I mean, it's a cross-sectional area at any point is always circular. So you have a circle here, okay. But as you look at different positions, you find the circle has different radius. So as you go down from the top of the container to the bottom, the radius of the circle shrinks until it reaches the very bottom, where you have a very small hole at the end where water comes out. Okay, now when you fill this open top container with water, water will drip out slowly from the small hole at the bottom. And the design is such that because of the shape of this container, okay, which we need to find out, we want to find out what this, what this curve is basically. As water leaves the bottom, you will find that the water level will descend at a constant speed, okay, constant speed. Now that is different from the first case. Look at the first case here. You already should know by now, with or without that cap, the beer level will not descend at a constant speed. Okay, initially as the beer level is high, you have a lot of pressure pushing things down. So water will come out, the beer will come out faster at the bottom of the container. So Y will decrease slower, but gradually, the speed of descending will slow down. So it is not a uniform descent. But here you have a uniform descent because the cross-section area of this container is not uniform, even though it's circular. It's not uniform in radius. Okay, so let's see how we can make that happen. How do we make dy dt a constant? Okay, the idea is the same. We still have to use the Bernoulli's equation. So you have to identify 2 points, one at the top of the container, one at the bottom of the container, 1 and 2. Okay, and we equate these 2 points with Bernoulli's principle, Bernoulli's equation. So let's do that. So here at the top I have P1. P1 is just P naught because it's open to the outside, the air pressure. Okay, plus rho g y. Y is the height of the water in the container. Okay, plus 1/2 rho v1 squared equals P2 at the bottom, but P2 is also equal to P naught because it's also exposed to the outside, plus rho g y2. Rho g y2 is just 0 because we are looking at the position of the hole, which is at the center of the coordinate system xy. So y equals 0, and then plus 1/2 rho v2 squared. Okay. Now, since the hole is very small, then the speed of the water coming out of the hole is much greater than the speed of the water descending at the top. So V2 is far greater than V1. So we can ignore V1. So set V1 roughly equal to 0. Okay. And you cross out the P2, then I lead to this. I need to rho gy is roughly equal to 1/2 rho v2 squared. That's pretty much the same as we had before. But what we want to make sure is that V1 should have to descend. V1 should be a constant. V1 is the speed at which the water level drops. So V1, which is dy dt, okay? Actually, it was a negative sign because V1 is just a magnitude is positive, but dy dt is negative. You want this to be a constant. Okay, now we know V1 is very small, but we want it to be a constant, a small constant. So how do you make that happen? Well, we saw V2 in the equation above, right? But here's V1. Now V1 and V2 are very different in magnitude, but they are related. How are they related? The equation of continuity. A1 V1 equals A2 V2, all right? And A2 is just the area at the hole of the hole at the bottom. I don't have to know what it is. I just know it's very small, but it's a constant. A1, on the other hand, is the surface area at the open top. And that does change. A2 is a constant, but A1 equals 2 pi x squared, isn't it, right? X is the radius of the circular opening. Okay, so now I have V2 equals to A1 over A2 times V1, and A1 is pi x squared, and then over A2, okay, and then times V1, right? Now V1 is a constant, that's what I desire. Pi is a constant, A2 is a constant, so therefore V2 is just a constant times x squared. Okay, that's what I want. Okay, plug that into equation. Let's call this equation 1. Okay, so here's equation 2. Okay, plug 2 into 1. Then I have rho gy, you can cancel the rho. You get gy equals to 1/2 v2 squared. V2 is pi x squared over a2 times v1. You want this whole thing squared. Okay, and that tells me how x and y are related. I can work this out. Then I find this to be equal to pi squared v1 squared to a2 squared, right? Just factoring everything out, and then x to the power 4. So therefore, I want y to be equal to pi squared v1 squared to g a2 squared, this whole constant times x to the power 4. This is the shape desired for this container. Y has to be a constant times x to the power 4. Okay, in order to guarantee that as the water comes out of the hole, the water level at the top would descend at a constant speed of v1. Okay, so this is the clever design to make this water clock work, and we utilized again 2 basic equations: the conservation of volume, or the continuity equation, that's equation number 2, and also the Bernoulli's equation relating the top and bottom of the water flow in a container.